name's Jameson Romeo Hall. I'm working with the Fairfield Group and VOES to get customers in the US and Canada over to ModelRisk. And you may have even heard from me if you're in the US and Canada, or you will be hearing from me. Thanks for coming to the webinar today.
And welcome everyone and thanks for joining us. So we are the Fairfield Group. We are a company that's focused on quantitative risk analysis, and we commercialize top-notch tools that generate this type of analysis for you in a very simple way. One of them is ModelRisk, and we're going to talk about ModelRisk today. ModelRisk comes from a company called VOES Software. VOES Software is a company based in Belgium, and what they did, they at the beginning were consultants, and after that, they became the software manufacturer of ModelRisk, right? So the ModelRisk has 19 years, if I'm not mistaken, this year, because this is from last year, so this is going to be 18 or 19 years in the market. And they also have two other products, one for schedules. For example, if you use Microsoft Project or Primavera, they have one software called Tamara, and the other is for an enterprise risk management. It's called Pelican. So VOES Software has these three software packages. Example clients, you have many different clients that they work with, and of course we help them commercialize software, do consulting, training, and so. Right. So what does ModelRisk do? ModelRisk do, and this is, remember, an introduction to ModelRisk. It does Monte Carlo simulation, and if you will remember Monte Carlo simulation, you will have a model, and that's any type of model. This could be for example, let me make it a little bit bigger. I don't know, an MPV model calculation, a budget model, an inventory model, right? A logistics model, anything that has potential additions of uncertainty. And what the ModelRisk does, it generates, right, inputs in the shapes of ranges. And that's what we're going to talk today. We're going to talk ranges, right? Ranges. So instead of you talking about, oh my, ranges, instead of you generating one deterministic model or one model with one variable and one value, right, we're going to talk about multiple values. And that means that if you have variable A, could be, for example, the price of the asset that you sell, or the price of the service that you sell. Variable B could be the quantity of clients. Variable C could be the churn, right, for a service. Or it could be the price of a given article that you sell. V is going to be the quantity, and C, for example, the inventory completion, the quality, etc. You can have as many variables as you want, and you can have as many distributions as you want. So what you will do is all these ranges that we're going to talk about, they could be translated and they could be replicated as distribution. So what's going to happen with Monte Carlo simulation is that I'm going to run a model that, for example, takes 1,000 iterations, and for each one of the iterations, the model is going to fetch randomly from each one of the distributions. That's what it's going to do. It's going to fetch randomly from each distribution. The model is going to connect to the variable, and the variable is going to fetch the information into the model. The model is going to recalculate 1,000 times. And after the 1,000 times, what I'm going to do, I'm going to add with a results table like this. And this results table, I'm going to analyze it as a distribution, right? As a distribution. So remember, of course, I can take the average. The average is going to be the mean, but no longer I will have the result in my Excel sheet. I'm going to use probabilities. And when you use probabilities, you use this type of graphics like histograms. So the moment that you move from your static model, remember a model that perhaps you have your MPV calculation, right? Or your risk exposure, which is what we're going to see today. That was one number, right? That was one number only. Now you have totally different things. Why? Because you added this volatility, you added this variability in the shape of distributions. The model is recalculating many times, and this is going to be cascaded into this results table that is going to be generating a histogram like the one that you see there, right? That's in a nutshell what Monte Carlo Simulation do, and in a nutshell what ModelRisk does, right? What else you can do? You can generate this on top of any Excel model. You have dozens of distributions. You can model scenarios, you can model correlations, you can model copulas, you have reporting capabilities, you have portfolio optimization, you can integrate with the Pelican and Tamara, as I said before. You have time series, data viewer, results viewer, etc. It's a very complete tool, all in one. You have only one version of ModelRisk, which is great, so you don't have to deal with the professional, universal, etc. You just have one version, and it sits all on top of Excel, which eases the learning curve a lot because you don't have to deal or to learn a new tool. It's just Excel, and it's an additional layer on top of Excel. Okay, now what we're going, if you are an at-risk user, as Jameson said, we used to work in a company called at-risk. So if you're an at-risk user, the software has a lot of easy to use options, like for example adapting the menu and converting it to a replica of what the at-risk menu should be, so you don't have an additional learning curve. Again, you can convert models from at-risk to ModelRisk individually or in bulk for a complete folder. You have better language support, and as I said before, one version only, full of features. Best thing, it costs like 30 to 50% less depending on the deal. So you can reach out to Jameson, or if you're in Europe, to our colleague Dan Goldbrum. Okay, now let's go with the topic of today. Every month we change the topic, and because we want a different application that is going to be included into this webinar. Why is that? Because of the really high adaptability and flexibility that this tool has. This tool is totally agnostic to industry, to content, etc. So the main idea is that we will bring problems or situations that our clients say they have, and we will reflect them here. So if you go to our YouTube channel, if you look for the YouTube channel of Fairfield Group, we already have like 10 different models that you can see. We have logistics model, workforce planning model, cost budgeting model, an NPV model, a cash flow, project portfolio model, etc. So we have a very rich library with all these videos that is available for you. Now, let's talk today about moving from qualitative risk, right? The typical risk matrices, right? Risk matrices, 5x5 scales, right? To quantitative risk, where we're going to have distributions and simulation. We're going to have a big result like this, right? That's what we're going to do. That's the main idea of today, right? We're going to talk from this little journey that we're all the time encouraging our clients, which is to move from qualitative to quantitative risk. Right? What is the project? The project that we're going to talk about is a data center. Why is that? Because you see that it's a trending topic right now, right? And imagine over 90% of the world's digital data has been created in just the last 2 years. All of that stored in data centers. The global data center market is projected to surpass $400 billion by 2030, growing faster than the construction sector. And data center electricity, which is a big, polemic topic right now, demand is expected to double by 2030, represented 2% of the global energy consumption, more than the airline industry. So this is something that is happening, right? And it's something that it's real. So if, of course, I imagine that you're familiar with ChatGPT or with the big clouds like AWS, like Azure, like Google Cloud, right? They all are stored in data centers. So that's the main idea, and that was the main idea of the project today. So what I did with the help of AI plus our experience, I generated this initial risk register. This initial risk register, which is here in this file, it's here. It has 20 risks And what we did at the beginning, we generated the typical classification, right, in a 5 by 5 matrix. That is the main consideration right now. 5 by 5 matrix. For example, insufficient cooling system capacity identified late in the design, which is something that hopefully doesn't happen to our data center, but it happens. I remember there was an airport that didn't have even air condition. HVAC precision units damaged during the transportation, which is very typical. Unexpected increase in steel prices, right? Failure in UPS system when you're accepting the UPSs, late delivery of switchgear, etc., etc. Typical technical from hardware installation to supporting platforms, etc. Everything that you need to create a data center. Right. So if you like, you can write to me and I can send you the file. More than happy to do it. Right. Now remember that this file has two scales of 5 by 5. Right. One is the probability, another one is the impact. And the main idea, and this is how we normally do it when we start with the risk management, right? What we do is we create all these matrices, and we assign these scales of 4, 3, 2, etc. based on this, right? So you have a probability, and normally when you ask somebody, so how likely is this for this to happen? And you say, oh, that's low probability. So the low probability will be between 10% and 25%. These are the rules of the game, right? And normally, and this is where it all starts, right? There are a few shortcomings that I'm going to mention about the risk matrices in a minute. But this is where it all starts, because we add this range to the to a probability label, but the probability label is a little bit more difficult to choose. I mean, it sounds really simple, but I think it oversimplifies the role. Same thing with the impact, right? A medium one is going to be between 2 million and 10 million, while a very high could be 25 million to 50 million. Let's say that our data center here, let's say it costs around 100 to 200 million dollars, right? So for me to assign these numbers and these numbers, right, I have these reference scales, right? The thing is that the reference scale it could be subject and it could be totally arbitrary, right? Now, what happens next? What happens next is that you will have, and I will show it to you here in my Excel sheet, you have a classification like this, right? Critical, high, medium, etc. That comes from here, right? Critical, high, medium, etc. Right? And depending on the product of the two, remember that you have 1 to 5 and 1 to 5. So depending on the product of the two, of course, you will have from 0 to 25, right? You will have a classification. And you will normally represent this with a risk matrix, right? That's how you would normally do it, right? You represent this with a risk matrix. Depending on the name, sometimes you have insignificant, or you have very small. You have a lot of different ways of doing this. I just went with a very simple one so everybody understands, right? And we don't focus on the qualitative, but on the journey to make it quantitative. Right? Now, once we do that, once we have this reference framework, right, that we have here, right, what we did is we created an inventory of all the risks, and these are all the risks located into the corresponding cell, right? So it's corresponding, for example, very high and high, we don't have a risk that it's 25, but we have a 4 and 5 that's going to be 20 and 20 here, right? So what are the main advantages, of course, of using a risk matrix? That it's easy to build, right? It's easy to understand, so people will understand it. So it really lowers the barriers to talk risk in a company, right? Support for early prioritization. So it's not going to be perfect, but people at least can think about it, right? In a less, I would say, subjective way, right? And it's a good foundation for evolution. So that's how I normally see it. I see all the risks here. I would say, well, this might or might not be the final risk that I would use, but at least it's a good preliminary risk table. So we will utilize it. We will recycle all this information and use it in a little bit, right? So this is one thing. Second thing are the limitations of the risk matrix, and I wanted to talk to you about that. Give me just 1 second. Give me just 1 second. I'm sorry, I had a lot of echo, so I needed to turn off my speaker. So now, what happens with this, right? We have the limitations of the risk matrix. So we talk about the good things about the risk matrices, but now let's talk about the limitations. A little bit, as I said, oversimplifications of reality, because you reduce the continuous probabilities and you just go to a number. It hides uncertainty, the same thing. Ranking distortions, right? Because different risks can land in the same bug despite radically different magnitudes. And this is one of the big things here. You see, you have a risk that it's 25 to 50 million and 60 to 80%. Right? Imagine it will land with a risk that could be, I don't know, 25 million, another one with 50 million. And you would think, and your reason would say, well, it's more or less the same. And maybe it's twice as much, right? You don't have aggregation capabilities because you cannot compute a total project or contingencies or P50 or P90. You don't have that. You don't have a distribution here. Remember, it's only deterministic numbers, and you don't have scenario. You can normally ignore correlations, multiple occurrences, and that, because normally you have this way of applying the risk, right? Let me go back here. See that you don't have a way of saying if this is a single or a multiple risk. It's just 1 to 5 and 1 through 5, like this. So you just have to be very careful with that. As I said, I don't like to discard it, all the things from the risk matrix, but you will have to know what are the limitations of it, right? So once you build it, of course, the risk matrix has the advantages that it has the attention of everybody. So it's a really good consolidation. It's a really good focus tool, right? Now, so what is it that we did? We created first an adjusted scale preparing for the conversion, for the probability conversion. So for example, for the very low, which was 0 to 10%, now we're going to convert it to 3. For the medium, 25 to 30 to 45, it's 35, 65 to 80, 70, etc. So we created these reference translations, right? And this is what I added here, which is important. This is the initial conversion framework, right? I'm not saying this is the final one, but the actual number, the one that you're going to run when you run the analysis, it should be the result of a deep analysis on a case-by-case, risk-by-risk, right? So I'm not saying that this is going to be the final one. Because of simplicity and time, today I'm going to use that. But you have to really consider that this is not the final one. This is the initial one. Right. Same thing with the impacts. You see, for example, in the impact, the very low, now it's a minimum, most likely a maximum from 100 to 500K. Right. The very low, it was 10,000 to 250. Right. So what we did, we make it a little bit bigger here. Why? Because maybe we were having the risks that were too marginal. They were over reflected here. And because you see, you have risks of $10,000, that could be the replacement of a, I don't know, of a camera for a warehouse, and $50 million, which could be a cyber attack of massive proportions, right? So which one is which? So it depends, and we will have to validate also in this case, the magnitude that each risk has and where it stands in your analysis, right? So we created this translation table, right? Translation table here, translation table there. This is something that you will normally do by hand, right? If you ask me, this is not something that you do mathematically and then you always take the average, right? I took the average in some of them because it was easy, but for example here from 65 to 80, I didn't put 72, I did put 70. And from 0 to 10, I didn't put 5, I put 3, right? So this is something that you will have to do on a case by case, right? And again, this is not the final number. This is the initial number. Remember, we're going to do the first jump, and this is what is about today, the first jump, right? For example, here, you see that in the model, we have a probability of 4 that is going to be 55%, and an impact of 4 that is going to be from 7 to 20 million, right? No additional one-to-one analysis were done, and that's very important to know, right? So that's the first step, the translation, right? We move from the qualitative to the quantitative in a translation, both for the impact per event. Remember, this is always the impact per event, and we're going to see it now per event, right? and this is the probability, and we're going to see that we can modify a little bit that, right, like this. Now, first step, normally when people do this, they say, okay, so what we're going to do the product of the probability that we did, remember, because we generated probability, times the impact. And for the impact, normally what they do, they choose the mean of the impact, and they multiply, I don't know, 55% times the mean between 7 and 20. Let's say it's 14 million, right? So this is going to be more or less, I don't know, 8 million. So this is the impact, and this is something that it's in the middle, right? I wouldn't say it's totally discardable. It could have an idea, but this is not what we're looking for. So don't stop there, because a lot of people, they stop here in the expected mean, right? And I did it here in the model. Here in the model, you see you have the minimum, the max, and normally what you do, you multiply the 55, remember, times the mean. Remember, this was 7 million, more or less, you see, and this is the average of these three, right? Some people calculate the mean times the medium divided by 6, etc. Some people calculate the PERT, etc. So don't stop here. Why is it that you have limitations on the expected mean? Yeah, you have a lot of shortcomings there. So why again, it hides variability. Why? Because we're taking numbers. We move from the qualitative scale world from 1 to 5. Now we're in the quantitative world. But in the quantitative world, we are wasting all this information and making it one dimension again. We're multiplying the probability times the mean of the impact, right? It hides the variability because I'm eliminating the extremes. It misses the tail risk, which is exactly what I said, right? You have a risk that was, remember, from 7 to 12 to 20 million, and what I'm doing is I'm taking the mean, I'm multiplying this times 55%. So I'm eliminating all of that. I'm discarding all this information. And I'm assuming linearity, right? Because I'm treating all probability and impact as proportional, which is rarely true. You cannot handle multiple occurrences, and that's what I did here. You see, what I did for the risks that are multiple, and we're going to see that in a minute, I multiply this by half of that. You see, but I have to invent something that it doesn't have mathematical support because it's not yet well built, right? Ignores correlations. It's not good for aggregation, so you cannot have a P50, P80, etc. Distorts prioritization. Imagine that you have a 10%, and this is what the product causes, and this is maybe the one of the main reasons is this, right? You will have a 10% probability on a 1 million risk, or a 1% probability on a 10 million risks. You see, and this is the same. And I'm not sure if I feel comfortable saying that this is exactly the same, right? Because mathematically the impact is going to be exactly the same. So, but I'm not sure if me as the product manager, as the project manager, as the owner of the company, I'm going to be handling this with the same level of comfortableness, right? And this encourages false precision, right? Which is this. It generates a numerical score that looks rigorous but lacks all the analytical depth. So please don't stop there. Go for the full simulation, right? So how is it that we're going to move to a fully quantitative risk approach, right? We're going to do a couple of things. First of all, we're going to talk about the risk type, because there are two risk types. Risks that occur once during the life cycle of the analysis, of the horizon of the analysis. For example, normally you would do it yearly. So if you do it yearly, so once a year, the risk will occur. Right? So these are single risks, and they use a Bernoulli distribution. The Bernoulli distribution only has the probability of occurrence and can occur only once or not. And risks can be multiple as well. And then if they are multiple, you're going to use something that it's called a Poisson distribution, which uses a parameter called lambda. And lambda is the average number of times that the event can occur. You see? So this is different. Now we added one dimension to the model. If this is single or multiple, right? The impact, we just have to verify. Remember that the impact that we had before, you just have to verify that the impact that you are using is the impact per event. Because sometimes people like to say, well, this could occur 3 times. So they could say this could be 9. Imagine each event could be from 3 to 5 to, I don't know, to $10 million if this occurs, right? But sometimes people would say, well, as this could occur twice, so it could be 6, 10, and 20, right? So people add up on the limit the number of times, the total impact, which is wrong, right? So don't do that. It's always the impact per event. That's the best way of analyzing the impact, right? Do an aggregation of for every time the risk occurs. So let me show you how it works. So this is what I call with aggregation of multiple occurrences, right? So let's say that we have a risk that has an average occurrence of 4 times, right? 4 times. So if the risk occurs, let's say, remember, the average occurrence is 4 times. That means that the average is here, meaning that you have less than 4 or more than 4, right? 95% of the time, and I know that you were thinking about that, you were thinking this is the maximum number of times. And we're talking about the average number of times, meaning that you can have less and you can have more, right? So what I will do is I will create, right? You see this variability there. So please take a look to this cell F4, right? Let me make this. Let me hide this so you can see this, right? Like this. So for example, if you have the risk 5 times, occurring 5 times, what can happen 5 times in the, for example, in the data center industry is that you have HR scarcity. Everybody's building data centers and you need the expert. The best experts are not going to be available unless you pay them a lot and you keep them. Right? So let's say that you have this with 5 people or you have this 5 times during the year. So the typical product, what's going to do is going to multiply this number 5, which is 5 times, let's say $180,000 every time that I lose one and I have to get another one. This is how much I have to pay the headhunter. So I just multiply this, and this is going to be 936, like this. You just have to multiply that. But in reality, what happens is that, you see, is that every time that this happens, you will have a different cost. Because one time this could be not the biggest CEO, but here maybe the CEO left. Here it was a senior engineer, a senior architect. You see, it's not always the same person. Right? Same thing here. If I go to another risk, for example, I have 3 risks. I can multiply this. It's 496. But imagine this could be the risk of, I don't know, an environmental penalty. Not always you're going to pay the same penalty, the same exact penalty, because maybe the damage is going to be different and they have some equation that calculates the damage. So you will have different ones. So it has to be, you have to be very careful with this, right? That not always you have to multiply this times that. You will have to generate this multiple occurrence samples, otherwise you're not being faithful with reality, and we need to hopefully make the model as real as possible. So that's another one, right? Like this, and this is what I just explained to you, right? That you can have the multiple occurrences there, right? And what's going to happen when we create all of that? So let me show you how this was created, and how can we get to this very nice histogram over there. First of all, we go here to the occurrence distribution. You see here, the occurrence distribution is the Bernoulli distribution that I mentioned before. The Bernoulli distribution can have only 2 numbers, 0 and 1. And the probability probability that I had before, right, the 55%, is going to be here, right? So take a look here. See which one. Oh, you see, I'm I'm trying to find my F9, or here, you see, sometimes I will simulate. Take a look here. I will simulate, and this is going to simulate the behavior of that. Sometimes this is going to happen, sometimes this is going to happen, sometimes this is going to happen. You see, so I'm simulating what's going to happen. Sometimes no risk occurs, meaning that you're not going to have any impact. But sometimes the risk occurs. And when the risk occurs, like for example here, you will have one risk times the output of this simulation, of this distribution, which is going to be 12 million. And sometimes you have 3 times, you see? You have 3, which are going to sum up 16. Sometimes you have 4, which are going to have 22 million, etc. So what you will have to take care is that for some of the risks, you're going to have a Bernoulli distribution, which are the single risks, you see here. For other distributions, you have multiple risks. So these ones in yellow, they will have the Poisson distribution. You see, Bose-Poisson distribution. So you can click here and take a look to the distribution like this. So this is a Poisson distribution with lambda equals 3, like this. You see? So as I said, as the average is going to be 3, more or less here, you see that this distribution can have up to 9 times or even 10 times, right? 10 events could happen with a Bose-Poisson 3, right? So this is the occurrence distribution, right? Which has the probability or the frequency. And you have the impact distribution. For the impact distribution, we're going to use a Bose triangular distribution, right? Like this. Normally, you would utilize a regular triangular distribution like 7, 12, 20, like this, and you will see it. You can see that here, right? This is the triangular distribution, 7, 12, 20, like this. What's going to happen, and why is it that I am using the object here? Because ModelRisk is going to do, remember, the multiple occurrences. So the multiple occurrence is going to be done by using something that it's called the aggregate MC. I'm going to show it in a minute. Let me see it here. It's called the aggregate MC, like this. And this lets you combine, you see, lets you combine the severity distribution, which was the triangular, plus the Bernoulli distribution. And this is going to automatically run a quick simulation and add it up right here. This portion over there for the aggregate is what I show you here in the multiple occurrence. If you want to simplify, let's say version 0 of the model, of course you can do the product. It's not going to be as accurate, but as a version 0 is going to be much, much better than everything that you had before. Right? So what's going to happen again is that you will see how this changes, how all these numbers change one by one, right? And you will have different outputs for that. So sometimes you will have 282 million. So maybe let's do this. Let's say that our data center is going to be costing a little more, 282 million. Sometimes you will have 200. Sometimes you will have 245, etc., etc. Right? If you do with F9, which I'm not sure what happened with the configuration of my laptop, I cannot click F9, so that's why I'm doing it like that. Right? So now that I have this, you see that I have the model and I extended the model, and that's what we did. I extended the model, added the probabilities and the occurrences, added the distributions. Right, so you will remember that you can do a Bose output here, and this output is going to take all the samples from the, let's say, 1,000 iterations that we're going to run. Right, so I will start and I will run 1,000 iterations. That means that I will recalculate the model 1,000 times, and these 1,000 times are going to produce an output, right, a result here. And this result, let me see it here, is going to be the total risk exposure, like that. The total risk exposure is going to go from 100 million to 369 million, right? So let's say that our data center costs $1 billion, right? which is all this scale, right, from min to max. Our mean is going to be 220 million, right? So if you want to budget how much money you're going to spend because of the risk, we're talking about 220 million. And normally here, what happens is that you try to compare it with the expected mean, right? If I didn't do this, remember that what I said before, that for the single risk, I just multiply the mean times the mean of the impact. If you don't include everything that you have here in color, the total is not 144, it's 67. So what I did here in color, I multiplied, imagine, I multiplied the number of occurrences that can happen times the mean of the risk divided by 2. Why? Because I didn't know which one to use, right? Because otherwise I cannot put full price here, right? Otherwise I will be considering that it always occurs, and that's totally breaking what you have here in the expected mean, that you're multiplying it by a probability. So that I divided this by 2 to have only a portion of it. And that's why this is flawed, to use the expected mean. So once we have this, so let me go back here to the results. What else you can do? You can calculate contingencies. You can say, well, I want to see what is my P80. Right? So my P80, I will go here in the markers and I will say add a new marker that's going to be P80. Meaning that if I want to be protected at 80%, right, I will have to have 255. So please remember, we started with 144 with this calculation of the expected mean, right? The mean was 220, which is more or less here. And then we have 255 of the P80. The good thing is that we can see it now. We can visually see it. Sometimes, and it depends on your audience, you need or not to include this type of graphic. Some people like to do it with this graphic, with the cumulative ascending graphic like this, and maybe you would like to add the mean as well. Right? So you want to add the mean, and you can see the complete progression, right? That, well, sometimes this happens, right? That you have the mean and the P80 very, very close to each other. That what you can do here, you say, well, I start with 3% in the expected mean. Actually, you start with like 67 in the expected mean. Then you added that. It's sometimes very difficult to calculate number, to understand it, because it's not as I would say as precise as the one that we're doing here. And then we have the mean, which was 220, right? Here, the mean was 220, and the P80 was 255. So if you like to have a contingency, perhaps you will have to ask, right, for maybe from 144 to 255, these 100 additional millions are going to be because of the risks that we added. Right? What else you can do with this? Because you have the in this case, the histogram capabilities, but another thing that comes with Monte Carlo, right, and which you don't have in the other methodologies, is the capability of doing tornado charts like this. So what you can do, I generated one tornado chart, which is called the proportional contribution to spread, which is basically doing an X-ray or a disaggregation of the risk. So the risk, if you sum up all of this, which is like 22 and 21 and 20, you have 60 and 80. Here, you already have the first 80% of the risk, right? So what this is telling you is which are the most important risks, which are my key drivers. So utility power connection delays, labor shortages, remember that we talked about it, rework in chill water, and BMS and PMS integration issues. This should be your focus, right? And this is going to give you focus. In these ones, you're going to put more of your time allocation, your cost allocation, you're going to put that there. You have more. You can do insert tornado chart, and you can insert another tornado chart. This is called the conditional mean, for example. And normally it will show you which is the scope of each one of the variables. Right? For example, the labor shortage, if the labor shortage is very cheap during the project, my total risk is going to go to 198 million. But if my labor shortage is very expensive, this can go to 250. So you have, you see, the two extremes over there, right? So it's important for you to know that you can measure that. You can measure the scope, and here you have, oh my, you have tons of different tornado charts. They added more in the latest version. So you have 5 here, plus 3, you have 8. You have the correlation, typical correlation tornado over there, right? And you can say, I just need the top 10, so you can do only the top 10. So you have a lot of different things to do. What else you can do here? You can copy this graphic. You can paste it in, I don't know, in my PowerPoint or anywhere that you want. Or even more, which is something I really like. For example, let's say that you like the results. So you say here, results. Right? So what I can do here, I can go to my cumulative graphic, and I go and I say home link chart here. And I insert this link chart like this. And this is going to copy, you see, this is going to copy this chart into my Excel, which is great. Why is that? Because next time I run the model, and the model is going to update this automatically. So you don't have to worry about copying and pasting and moving the model from platforms, right? So with this, you see, in these 45 minutes, the main idea was to show you how to move from a qualitative world to a quantitative world in a very simple, with a very simple translation table approach, skipping the expected mean, but talking about it, and also taking a look to what the main shortcomings of the methodology could be, and of course all the things that you need. Now, model risk, as you see, we only took into consideration 2 or 3 things from model risk: how to select a distribution, how to set up inputs and outputs, how to view functions. Remember that we view a few of the functions and run the simulation. So our main idea with this is to invite you to take a look to model risk and how it does work. It's a really neat tool. It does the job. It's really, really simple, right? And you have full traceability. So let me show you what you have in traceability. You can go here. You can go to insert and say, I want to see here insert the data list. So the data list is going to show you, you see here, is going to show you the impact and see, for each one of the risks. So you have the insufficient cooling, you see here the impact, you have 0, 0 because the risk didn't occur. But for labor shortages, it's always occurring. That's why you have such a big impact on that one, right? And then you can always copy this, copy all, you can copy that, move it to Excel and analyze it one by one and see if this could occur. You see that perhaps this risk and this risk, they cannot occur together because you have some controls or mitigations that are going to make for this to happen together. You can run some statistics as well, you can run scatter plot, etc. Right? What will be the natural next step here, right? Because we just have one snapshot of our data center model, right? And this is what we call our current risk, right? This is going to be the current risk. So normally what you do, you generate this snapshot, you do the analysis as I did here, and then you go next, and then you do the target risk. But to move from the current to the target, normally you will have to add some mitigation or some controls. And these controls are going to accept the risk, add consulting companies, buy insurance policies, etc., etc. You have to spend money, right, in order to decrease whether it is the impact or whether it is the probability or the frequency, right? So if you want this change, you have to spend some money, and then you recalculate the target risk with the new probabilities, the new frequencies, and the new impacts. And then hopefully what you will get, right, now that we have something that was like 200 and, oh, sorry, let me do it again, like this, right? And then you have something like this, and you had 255 is the PAT. what you will be expecting is something like this, right? That's going to move to the left because of all the controls and the mitigation, and maybe this is going to be 210. Who knows, for the new P80, right? And that will be the next step.